Hello and welcome to this video. In this video we're going to look at Kirchoff's laws. So in the introduction video we did a little bit of recap into how electricity works in both series and parallel circuits. Now we're going to introduce Kirchoff's laws, which are going to explain in a little bit more detail why we know those things are true. And then a little bit later we'll get on to looking at how resistors behave when they're in series versus parallel as well. So Kirchoff's laws state that we have two of them. So Kirchoff's current law is the law that tells you how current behaves in both parallel and series circuits, and it basically says that if we have a junction, the sum of all the current coming into the junction has to be the sum of all the current coming out of the junction, okay, at any junction. Okay, this means if I have a point here and I have a current I1 coming in, and then that splits off into I2 and I3, then applying the current law means that I1 must be equal to I2 plus I3, okay, because all of the current coming in has to be equal to all of the current coming out. Now this is true because we're using this to conserve charge, okay, so this is just a conservation of charge. We're saying if we have charged particles, being electrons, coming into a circuit, we're not going to create any electrons here. We're also not going to destroy any electrons here, so the amount of electrons that come in has to be equal to the amount of electrons that come out, and this is all this is using. So the current going into a junction must be equal to the sum of all the current coming out of any junction. Okay, this is going to explain how current works in both series and in parallel, because if we had a series circuit, okay, so I'm going to use the series circuit with two fixed resistors, the current coming around here never meets any junctions, okay? The current doesn't split anywhere, which means that there is no current going out. So if the current coming in is just the same as the current coming in, then it always has to be the same at any point. It only ever splits when we meet a junction, which is reinforcing what we already knew, which is that current is the same everywhere in a series circuit, okay? It's also going to explain why current splits in a parallel circuit, and that's because we do have junctions in parallel circuits. Okay, we have this junction here. So if I had, for example, I1 coming into this junction, it's going to split into I2 and I3 because the electrons can take different paths. And then this means that the sum of these two currents, I2 and I3, has to be equal to the sum of the current coming into the junction, which is I1. Okay, this is why the current between these two things will be different, because we're just splitting the amount of electrons that are traveling down each path. And this is Kirchoff's current law. So we now know a more in-depth detail explanation as to why current behaves like this. We can now look at Kirchoff's voltage law. So Kirchoff's voltage law is slightly more complicated, okay, but it's also slightly more useful, I would say. So Kirchoff's voltage law states that the sum of all of the EMFs must be equal to the sum of all potentials in any loop. Okay, so it's first we have to kind of define what is the EMF. So the EMF is basically the work done per unit charge going into the circuit, whereas the potential difference would technically be the work done per unit charge the circuit. Okay, so this would be the difference. So the EMF works at places like a battery. Okay, so the EMF would be all of the charges that come in, we're charging them up, we're giving them, they're gaining electrical energy. As soon as they have some potential difference, that's when they're going across a component where they're going to collide and they're going to lose energy. So EMF is when the electrons gain energy, the potential difference is when they lose energy. And we're saying that the total energy gained in any loop has to be equal to the total energy lost in any loop. Okay, and this is just the conservation of energy. Okay, so we're literally just saying that the amount of energy we put in has to be the amount of energy we get out. Otherwise, we'd be creating energy from nowhere, and we know the very, very fundamental law of physics is that energy cannot be created or destroyed. So how does this then tell us what we know about these circuits? So if we look at a series circuit, we'll take the same circuit again. We'll have it with two resistors. We know this battery is the only thing providing the EMF, okay? But we have two sources, we have V1 and V2, both providing some potential difference. This means that if the total amount of energy we're coming into the circuit with is the EMF, it has to then be equal to the sum of V1 plus V2. Okay, so this is why the potential that we get into the circuit is split between these components in series. Whereas if I looked at a parallel series, a parallel circuit even, I would have to choose an individual loop. Okay, so let's say I chose this loop. Okay, the EMF here is only actually being lost over one potential here, which means the EMF has to be the same as this potential. I could also choose a bigger loop and go around the very outside of this, and this potential would also have to be the same as the EMF. And then you might say that surely if we have a EMF here or a loop here, then this doesn't work anymore because we don't have any EMFs, but we have two potential differences. We can easily solve this by saying that if we think about how much energy the current has at each point, at this point we're going to say that it has a very high energy, and then it gains and then it loses energy, and in this is going to be the same. Okay, I'm just going to get rid of this V. But if we trace around this loop, it means that we're starting at this point. So what this is going to look like is essentially as we go across here, we've actually gained potential. Okay, so this is why the direction that the loop is very important, because it looks like we've gained potential across here, so it acts as an EMF source, and then we've lost potential across here. And the potential that we gain across here has to be the same as we've lost there, and therefore it still works. Okay, this idea of putting in this loop between two things with no EMF is going to turn out to be incredibly useful when you look at circuits. So if you had, for example, if I draw out a new parallel circuit and we had, let's say we had two resistors here that were in parallel also with two other resistors. Okay, and let's say this point here was called X, and this point here we'll call Y, and this was 5 volts across here, and this was 4 volts across here, and there were 3 volts across here, and there were 4 volts across here. They might ask you, what's the potential difference between the points X and Y? Okay, to do that, you can then just say, let's have this loop. We know we've got an EMF source that's acting as 3 volts. It has to be lost as 4 volts, so the difference between here has to be 1 volt. Okay, that might seem pretty obvious from the fact that it's 5 and 4 and then 3 and 4. They both have a 1 volt difference, but it's actually much more useful to be able to prove this using Kirchoff's voltage law. Okay, so with Kirchoff's laws, we are able to then explain how current behaves in both parallel and series circuits, and how potential or voltage will behave in both parallel and series circuit. I'm actually going to split this video, and I'm going to do a separate shorter video looking at how the resistances of things in parallel and series will work. So we'll stop this video here. In summary, the Kirchoff's laws and the Ohm's law are the three fundamental laws that are going to govern all of your electricity knowledge. As long as you understand and are able to apply these three laws, you should find a lot of these electricity questions very easy. Thank you for watching.